For this video, we'll do a similar comparison of weak bases, what we just described in our previous video with weak acids. And realize that for this class, most of the examples we're going to work are weak acids, but I do want to start by describing the similarities between their weak acids and weak bases. So for a weak base, we will be given a base ionization constant, a Kb value, that again is a constant value until we change temperature. So here again, weak bases are weak because they ionize or dissociate very little, only about 5%. And all of their calculations are similar to those of weak acids. They set up ice tables, we have equilibrium expressions, we solve for X to find pH. The one key difference, of course, is that in a weak base system, we would solve for hydroxide concentration, meaning that in our last step to solve for pH, we would have a few more steps to go through. This equation, again, is our general or generic base equation. So if I gave you trimethylamine and a Kb value, the Kb would tell you that it's a weak base. You wouldn't know what that formula is necessarily, and so you can use the generic capital letter B to represent a base. When it dissociates in water, of course, our conjugate acid, we add the H onto it, and producing the hydroxide confirms that it is a base. Like we saw with acids, we realized the larger the value of Kb, the stronger the base. And we could calculate a pKb value by taking the negative log of Kb. Again, P, that little P in front, means we're just taking the negative log. Some examples of weak acids and weak bases are worked examples 10 and 13 in the OpenStax book. And again, a table of bases for you. Recognize that this is much shorter than our list of acids. Also recognize the word amine in a lot of these. Again, that means it is derived from ammonia. Notice the other ones, although they don't have the word amine in them, they have that same ending and they contain nitrogen. So everything is derived from nitrogen and its lone pairs. And again, as Ka values go up and increase, our pKb values decrease, an inverse relationship there. For bases, we can also calculate the percent or degree of ionization or dissociation. Same idea in our equation, except specifically for bases, because we're solving for hydroxide at equilibrium, we would put the hydroxide over our initial base concentration. Again, our setup for this would be simply the X value divided by our initial concentration times 100. And again, it is the exact same setup as solving for X when we check our assumption. And to make sure we know how to do that setup, we're going to go back to our ammonia problem when we solve for that pH to solve for the percent dissociation. And so in this one, when we solved for hydroxide, we got a concentration there of 8.4853 times 10 to the minus 4 molar. Remember our initial, that was at equilibrium, and our initial base concentration was 0.040 molar. So our setup for this calculation, of course, would be the hydroxide divided by the initial base times 100. And again, we did this calculation on that slide with the weak base, but here we're doing it in a different context to calculate the percent ionization. And now we are going to report for sig figs. So because of our concentration, we go to 2, and this one had a percent dissociation of 2.1. And again, on this graph in the bottom right corner, we can see again the same concept applies as we change concentration. In fact, as we're diluting a solution, moving to the left, lowering the concentration, our percent ionization increases.